Hi everyone, I'm Juan Montesinos and I'm glad to be here to present VoViT, low latency graph-based audiovisual voice separation transformer. Voice separation translates to isolation of a target voice in a mixture of sounds. Let's listen to an example. In this case, we can observe a challenging scenario, 5 different voices and 3 instruments. Our goal would be estimating the voice corresponding to the guy within the orange box. On contrary to many works, we don't rely on raw video to do so. Instead, we propose to use face landmarks. Face landmarks are a graphical representation of the motion and the spatial structure of the face. This way, we can reduce the storage cost of the data, the computational cost, and the overfitting, allowing the network to be trained on small datasets. Besides, face landmarks are cheap to compute and preserve user identity. The most common approach to address source separation problem is to estimate a mask such that, once multiplied to the spectrogram of the mixture, returns the isolated voice. To solve the problem, we designed VoViT. VoViT is a multimodal deep neural network which operates in 2 stages. In the first stage, 2 encoders consume the phase landmarks of the target speaker and the mixture spectrogram. Both encoders are designed to preserve the temporal dimensionality. Then, the resulting audiovisual signal is processed by a transformer in 2 different ways or paths, frequential and temporal. In this stage, we minimize the mean square error between the ground truth complex mask and the estimated one. Complex masks give to the network the capability of tuning the phase of the prediction, which improves the quality with respect to methods applied on the magnitude spectrum only. At this point, we have a very good estimation of the isolated voice. However, we can still hear attenuated interferences. In the second stage, we use audio-only network that learns to enhance the lead voice. This is, suppressing the remaining interferences. This is just a small encoder-decoder trained to predict binary masks. We test and compare our model in 2 different scenarios. On the one hand, we train the model on a huge dataset with more than 2,000 hours of speech. The model attenuates way better the interferences compared to previous state-of-the-art models. Let's hear a real-world example.
I'm just glad that I've been able to remember my materials.
I didn't know that. I didn't know that. And they didn't know that I didn't know.
Next, the separation carried out by previous state-of-the-art method.
I'm just glad that
Later on I found out they were Mexican. I didn't know that. I didn't know that. And they didn't know that I didn't know, and that's...
Our estimation...
I found out they were Mexican. I didn't know that. I didn't know that. And they didn't know that I didn't know.
This is a challenging scenario, as there is a side view of the speaker. Since we estimate 3D phase landmarks, we better capture the motion information. We hypothesize this is the reason why our system models the silence of the target voice at the beginning of the sample successfully. We also test the model for singing voice. Singing voice separation is a tougher task as there are sustained notes and usually way more events in the mixture.
Oh, yeah, baby, whip it to me.
Next, we are going to hear Wynette's estimation.
Oh, yeah, baby, whip it to me.
You will find our estimation, compared to the previous state-of-the-art, has way less interferences. Let's hear it.
Oh, yeah, baby, whip it to me.
Lastly, we analyze the similarity between speech and singing voice. The results on the table shows how models trained on speech generalize poorly to singing voice. Thank you for attending and feel free to visit our website for more code and demos.